let x approach a number. So we were looking at limits as x approaches a particular number or point of interest when we were looking at a graph. And the results were that y became arbitrarily large. So we had a vertical asymptote because we had a y that went up to infinity. Okay, in today's section, we are going to look at let us have x become arbitrarily large. So now we want a limit where x goes off into infinity, and what happens to y. So here I have a function f of x equals x squared minus 1 over x squared plus 1, and I'm interested in what is this limit as x approaches infinity. So we're going to do some not guess and test, but we're going to do some calculations using a table of values. So if you guys could grab a calculator and let's test some large numbers. Bless you. So remember that when you are typing in a function that has a numerator and denominator, we are using brackets for top and bottom. So when I go to y equals, we're having brackets, x squared minus 1, close the bracket, divided by, oh, I'm missing a bracket in here. Let's try that again. Bracket, x squared minus 1 divided by x squared plus 1. Close the bracket. Table, let's start with 0, or I already know what 0 is. So let's do 10, 100, 1000. And my calculator can't round off that many, so it's already giving me a 1 here. But it's saying that this is going to be 0.9802, 0.9998, 0.999, ... Okay, do we see the trend? As we let x approach infinity, our y values end up approaching positive 1. Now, this is a symmetric graph. Notice that I have an x squared. These are x squareds. So I'm looking at a function that kind of looks like this. And of course, you can use your graphing calculator to test this. At negative or 0, x equals 0, my y-intercept is negative 1. And then it's increasing in value as it's getting large and large and large, right? This is x going off into infinity. However, it is approaching the value y equals 1. So this is a horizontal asymptote. You can also let x approach negative infinity. And again, just grab your calculator and make all these numbers negative. See if that changes the values. If I have negative 100, negative 1000, it's still giving me the same numbers. So that means, again, I have a symmetric graph where the left side of the graph is kind of doing that too. Approaching but never touching my horizontal asymptote as x goes to negative infinity. So my final statement is this. The limit as x approaches infinity of the function x squared minus 1 over x squared plus 1 equals 1. The limit is approaching 1. Therefore, we have a horizontal asymptote. Okay, so our theorem here in general, if the limit as x gets arbitrarily big, so as it goes off to infinity, if it equals a specific value L, this indicates that we have a horizontal asymptote. Okay? Now again, remember when we did vertical asymptotes? As x approaches some number, we had the graph going up like this and sometimes down like this. The same could be said for horizontal asymptotes. So whether it goes off in the negative direction or positive direction, we are going to have different looking graphs. But the idea is we are looking for some horizontal value, some number L that the graph will approach. So like this and like this could be an option. Okay. So the horizontal asymptote requires that x go to infinity. And I'm saying this 3 or 4 times because this is a very, very, very common thing that students forget. What is the difference between a horizontal asymptote and a vertical asymptote? When we are testing a vertical asymptote, we are letting x approach a specific number, because when we have a vertical asymptote, we describe it as x equals something, L, right? So as as the limit of x approaches I guess this would be x equals a, my bad, sorry about that. As x approaches a of a function, if it goes off to positive and negative infinity, then we have a vertical asymptote because the function is going off into infinity. However, if we let x go to infinity and the function gives us a number, then we have a horizontal asymptote at y equals L. Okay, so note the differences. Where is the infinity sign? For vertical asymptote, we're testing a point. For horizontal asymptote, we are testing the ends of our graph. What happens at infinity? Okay, let's take a look at this here. Find the infinite limits, the limits at infinity, and the asymptotes for the function shown. You do not see a function, so let's draw one. I'm going to zoom in here. I'm going to use maybe my blue pen, and I want you to, I'm going to use my black pen to make my scale. So every 2 boxes is going to be 1. -1, -2. Same with the horizontal direction. This will be 1, 2, 3, -1, -2. Okay, and let us make I'm going to do this like this. Can you make that shape? 1, 2, 3, 4, 5 boxes in, 2 boxes down. You see this shape? Can you draw that on your graph? I'm going to draw a second piece as well. Oh, I said I was going to do this in blue so you can see it easier. Let's do that. Okay, and then I'm going to have it cross over at this point. That way. And let's go down this way. And this way. Okay. Can you match up your picture with my picture? So this is an example of if I were doing your project where I'm drawing a graph and asking questions about it. I don't really know the equations for any of those functions, but that's all right. I can still tell you lots of information by analyzing the function. All right, let's take a look. The infinite limits. Infinite limits. In other words, we are looking at vertical asymptotes. Let's find those first. I see something going on here and something going on here. So the way I would describe this is by looking at the limit as x approaches, what's that first circle? Negative 2.5. Negative 1.5, thank you, sir. Of the function f of x. I don't know the equation for this function, but I can describe the behavior. It's going up. So I have positive infinity here. I could also break this down. I could have said what's happening at negative 1.5 from the right, and then what's happening as we approach negative 1.5 from the left. But as you can see from the left and from the right, they're both going up to positive infinity. So I can just talk about the general limit as we approach negative 1.5. However, where is my other limit here? At 2.22. Negative 1.5 is my first vertical asymptote here. The next thing I'm going to talk about is what happens as we approach x equals 2. Now here I do have to specify which direction because my arrows are going off in different directions, right? So as I approach it from the left, my function goes off to negative infinity. And as I approach it from the right to positive of f of x, we are going to positive infinity. So from the left, the function goes down forever. From the right, the function goes up forever. Okay, those represent my vertical asymptotes. VA at x equals positive 2. Here it is. So now what I'm going to do is I'm going to look at what happens at the graph at the very far left and the very far right. So this is what I'm going to look at, the limits to infinity and beyond. Okay, I'm going to infinity. I'm not finding where is the function at infinity. Okay, so this is where I'm looking for horizontal asymptotes. So what is the graph doing as x goes off to negative infinity? So goes off and to the left forever. It is approaching, my horizontal asymptote here is at 2. So this is my first horizontal asymptote, y equals 2. what happens the limit as x approaches the positive direction? So what happens on the right side of the graph? It's going off into 2.5. So it's approaching the line of 2.5. So I have another horizontal asymptote at y equals 2.5. I want to talk about some misconceptions when we talk about different kinds of asymptotes. You'll notice that the horizontal asymptotes are not the same. They don't line up. They don't have to. When we're looking for asymptotes, we're only interested in what happens at the very, very far right and the very, very far left. What happens in the middle, not really important, or at least not of interest to us. When we're looking at what happens to the function at infinity, it could give us two different numbers, and that is okay. We're just saying what is the number approaching. Vertical asymptotes, however, do have to obey the thing going all the way through. Okay, so it's possible to cross over, like you'll see in the middle section here. Here's my horizontal asymptote, right? Here's my horizontal asymptote, but I still have stuff happening in the middle. Thank you. Right? However, in the vertical asymptotes, I do not cross over those lines. Vertical asymptotes represent non-permissible values in my equation. They represent points where I cannot divide by 0, so at no point can I cross them. Horizontal asymptotes only affect the outsides of the graph, so whatever happens on the inside, I can alter. Okay? Questions, comments, concerns? So this was a visual demonstration. Let's take a look at an algebraic one. Example 3. What happens as we approach infinity of 1 over x? Some of you will recognize this as our base rational function with 1, 1, negative 1, 1, where this goes this way and this way, this goes this way and this way. Whoops. So as x approaches positive infinity, my limit approaches what?
0.
Goes to 0. And looking at the left side, also 0. If I had a function like what is the limit as x approaches infinity of 1 over x squared? Remember that graph? What does this one look like? Yeah, where the left side is flipped. So we're looking at something like this. As we go to the right, we approach 0. As we go to the left, we also approach 0. Okay, sometimes visually it's easier, sometimes algebraically it's easier, sometimes table of value is easier. You're going to have to kind of choose your own adventure as to how you solve these kinds of questions. Here's a box of importance. If r is greater than 0, i.e. a positive number, and is irrational such that we have 1 over x to the power r, the limit as x goes to infinity is going to be 0. Meaning for any rational function, 1 over x, 1 over x squared, 1 over x cubed. Right? If r is greater than 0, is a rational number, then the limit as x goes to infinity will approach 0. If r, a rational number, is such that x to the power r is defined for all x's, so it's in the domain, then going to the left will also give you a limit of 0. Yes, sir. No, because, great question. If I have x to the power of negative 2 like this actually flips the function to make it positive. So this would be parabola. So it has to be a positive number. Say that again. Because we are testing where the horizontal asymptote is. The whole point today is taking x to infinity to see if it reaches an asymptote. If x does not approach a solid number, that tells you that there is no horizontal asymptote. And we're going to do an example here. Let's go to the next page. Example 4. Evaluate this as x goes off to infinity and indicate which properties of limits are used at each stage. Okay, I am going to show you how to do this strategically in order to make it a lot easier on yourselves. So I'm going to make a note here, strategy. When you have a rational function, means you have x's in the denominator, multiply top and bottom by 1 over x to the n, where n is highest degree in denominator. Not overall, but just in the denominator. So when we have a rational function, we're going to multiply top and bottom by 1 over x to the highest degree in the denominator, and I will show you what that does. So let's take a look here. What is the highest degree in the denominator? 2. So let us multiply the top by 1 over x squared and the bottom by 1 over x squared. Okay, this is like saying we're multiplying by 1. We're not changing the value of the function, we're changing how it looks. If you did that, what would you get? The limit as x approaches infinity. Look at the top. What would that give you? Multiply it through. What's the numerator going to give me? 3 minus 1 over x minus 2 over x squared. Good. Okay, denominator. 5 plus 4 over x plus 1 over x squared. Okay, it looks a little bit uglier, but think of it this way. What happens when we have a denominator that gets incredibly big? What happens to a term? It goes to 0. So that means these terms that have an x in the denominator, x is going to get so big that these numbers are going to get so small, they are basically irrelevant because they are going to approach 0 so fast. The only things that don't change are the values that do not have an x next to them. And so we can say this limit approaches 3 over 5. So this is our horizontal asymptote. Yes, sir. Yes. Doesn't always work, but yes, in this case you could. Okay, are we comfortable with what I did there? Could replicate it on your own? Okay, so don't forget this strategy. It's a good one. It helps in many tricky situations. Okay, find the horizontal and vertical asymptotes of the graph given this function. Remember that vertical are non-permissible values and horizontal is the limit as x goes to 0. Okay, so we're going to do two different things here. Sorry, thank you. X goes to infinity. I wrote it and then said the wrong thing. Okay, let's take a look at the function. What is my restriction? X cannot be 5 over 3. This represents a vertical asymptote because I cannot approach that point. However, I can figure out, in this case, looking at the top, I have a radical, so I know I'm not going to be able to cancel it out. So it's not a whole, it's a vertical asymptote, goes on forever. So that part's done, easy. Let's take a look at what happens as x approaches infinity. And let's do square root 2x squared plus 1 all over 3x minus 5. Okay, let's do our strategy again. 1 over x times 1 over x. This is going to be 3 minus 5 over x. In the top, I'm going to remind you of some rules. I can take that 1 over x and I can put it under the square root sign as long as I do what to it first? One over x times 2x squared plus 1. How do I take this x and I want to put it inside the square root?
Oh, you make it square.
I have to square it and then it can go inside, right? So now do that in your head. If I square it and I put it inside, what does my numerator look like? 2 plus 1 over x squared. Did we all follow that?
Yeah.
Good. Okay, so now if I let x go arbitrarily large, this goes to 0, this goes to 0. So that tells me that the limit as x gets arbitrarily large and goes to the right of this function is root 2 over 3. Now we got to check the left side. So this was the right side. Let's do the same thing for the right, or sorry, for the left. X goes to negative infinity. This one is going to be slightly trickier because we have a negative sign. X is getting gigantic, but negative gigantic. When I multiply both sides by 1 over x, or sorry, both top and bottom by 1 over x, before I do so, yes, I'm going to multiply by negative 1 over x because I'm getting into a gigantic numbers on the left side of my graph, so I'm going to make it negative. Let me see if I did this right. Square it. Yes, okay. So in my brackets, because I have to square it to put it into the square root, this is still going to be 2 plus 1 over x squared. The bottom, negative 3 plus 5 over x. Did we follow that? Yes. Okay, so this goes away, this goes away. So my answer here is negative root 2 over 3. Yes.
Can we substitute infinity and negative infinity and then we like take the highest degree of both the numerator and denominator? And then we cancel out infinity again.
Yes. Doesn't always work though, but yes, that is a good strategy. Sometimes it doesn't work because sometimes you're going to have the same degree in top and bottom, and then what do you do?
What is the ratio?
Strategies. Okay, so we have 2 horizontal asymptotes and 1 vertical one. So let's write a concluding statement. Horizontal asymptotes. X, or sorry, oops. Horizontal is y. Y is root 2 over 3 and positive root 2 over 3. And the vertical asymptote is x equals 5/3 for this graph. All right, let's do some more fun things. Example 6. What's my strategy here? You think it's going to be a negative? Just infinity.
No, there's, you just subtracting an infinity from the rest of the functions minus x. It's gonna be a negative number.
Your hunch is correct.
It's infinity minus infinity.
Right. However, here's something that we can't do in mathematics. If we have a situation where we have infinity over infinity or infinity times infinity, we know this is just going to be a bigger infinity. This is going to be an infinity slightly smaller depending on this and that and the other.
Wait, infinity divided by infinity is just infinity?
Yes.
Isn't it one?
Shouldn't.
No, because it's not
Oh,
the
right.
same infinity.
It's not defined.
Infinity is not an actual number, and this is why we have to use strategies. If I say infinity plus infinity or infinity minus infinity, like in words, we kind of know what we're doing, but mathematically, this doesn't make any sense because infinity isn't a number. We cannot add, subtract, multiply, divide them in the same way that we do integers and variables. So this is why we have to come up with different strategies in order to make this mathematically make sense, mathematical logic, in order to come to a conclusion. So we can look at this and kind of have a hunch that this is going to be 0, but we need to mathematically prove it. Okay, so let's do a proof. If I put infinities in here, I'm going to get something that looks like this. That's not helpful. I don't want that. So what can I do? I want it to kind of look like this, because then I can cancel stuff out and make things go away. So what I'm going to do is I'm going to rationalize it and force it into a fraction. So I'm going to have x squared plus 1 plus x over x squared plus 1 plus x. This will give me limit x as it goes to infinity. My numerator will be x squared plus 1 minus x squared. All over the denominator will be x squared plus 1 plus x. And I can simplify the top further. This x squared cancels that x squared. So I have 1 over x squared plus 1 plus x. This is a rational with a radical inside of it. I'm going to use my strategy here. What's my highest degree in the denominator? Don't say 2. 1. Why is it 1? Because the square is rooted. So my degree is actually highest degree is 1. So let's multiply 1 over x, both top and bottom. And I have x going off to infinity. At the top, I'm going to get 1 over x. And at the bottom, we're going to put this into the root. So I'm going to get 1 plus 1 over x squared plus 1. This will go to 0. This will go to 0. And it will mathematically go to 0. I'm not saying that this is infinity, right, which is like an arbitrarily large number. I'm saying it will hit 0 as x goes to infinity. So in this sense, I have the limit as x goes to infinity. If I'm going to simplify this, 0 over root 1 plus 1, which is just going to be 0. Okay, things that we want to avoid. Things to avoid. We want to avoid a situation where we have 0 over 0 because we cannot divide by 0. We want to avoid situations where we have a 0 in the denominator. We want to avoid infinity over infinity or any of the other terms of infinity because it's not a real number. Okay, so the reason that I'm showing you these strategies is because a lot of students will look at this and say it's 0 and look at this and say it's 1 and it's not. Okay, so these are mathematical ambiguities that we want to avoid. So we're using strategies to show up and have concrete numbers in our equations. Okay. The limit as x approaches negative infinity of e to the x is 0. This is a fact. That's why it's in the box. And I will remind you that when x is 0, e of x is 1, and then it goes like this. So as x approaches negative infinity, the function approaches 0. So what happens, knowing this fact, when we have the limit as x approaches 0 from the left side of e to the 1 over x? It's the xth root of e, yes.
Wait.
Have a discussion quick. What do you think is going to happen? What is the xth root of e as x approaches 0?
It's 2.10 something. It's a sad number.
I'm going to give you your first step.
Are we multiplying? Oh, okay. Substitution.
Let's use substitution. Substitute t equals 1 over x. Then what would you get?
E raised to power 2. Oh, okay. So we're basically using the same formula where like we're multiplying the highest power as in the denominator.
Is it 1?
No?
Okay, think of it this way. If t equals 1 over x, okay, and we have, so then when x approaches negative infinity, t must approach what number? Sorry. I'm looking at the wrong spot. This is what I'm interested in. If x approaches 0 from the right,
It reaches infinity.
which one?
Because 1 over x reaches infinity when it's getting closer to 0 from the right. Oh no, are we looking at it?
From the left?
From the left is going negative infinity.
Negative infinity.
Never mind, I'm looking at.
Okay, so as x approaches 0 from the left, if t is 1 over x, then we are going down forever. So t is approaching negative infinity, right? Our substitution is drawing us this picture, right? So now let's substitute our limit. Our limit now is of e to the power t. And now instead of x, I'm looking at t. And instead of approaching 0 from the left, I'm approaching what? Negative infinity. So what's my answer? 0.
Oh.
Right? It's a bit of a, well, yes.
Oh, so as we substitute 1 over x for t, the limit.
When we do a substitution, your limits and your restrictions must change with your substitution. So if you make a substitution to make it look like the box, because we want to make it look like this, we have to focus on the restriction as well. Okay, box of information.
Box of information.
Yes. I evaluated it using substitution. I substituted the exponent, and then I substituted the restrictions, and this picture matched the box of information over here. So if you did not match the restrictions, then you would have to do some calculations. But as long as you match the restriction, as x goes to negative, or as x goes to 0 from the left, what happens to my substitution? It goes to negative infinity. So you got to substitute, if you do substitution, you have to substitute your term, whatever you're substituting, and you have to make sure that the limit matches your substitution. Again, these are all strategies. We're going to get lots of practice with them. Okay, box of information, please. The notation, x goes to infinity of f of x equals infinity, is used to indicate that the values of x become as large as x becomes large. So meaning it goes up forever or down forever, and there's no asymptote. Okay, so here's different ways that we can signify this. Right, so this is saying as x gets smaller, f gets larger. So it's going up and to the left. This is saying it's going down and to the right. This is saying it's going down and to the left. It's going on and on forever, no asymptotes. So if you hit a number, 0 or anything else, then you have an asymptote. If you get infinity, then you don't have an asymptote. So let's take a look at these examples here. We know that a cubic function visually looks like this. So as x gets large and goes off into infinity, the larger number that I put in here, the larger the result. So that means the limit as x approaches infinity of x cubed is infinity. It goes on and on forever. It just gets massive. Same in the negative direction, right? The limit as x gets very, very small. Oh, I wrote my arrow in the wrong way. Goes off into negative infinity of x cubed. My numbers get negatively large. Go off into infinity as well. So the left side's pointing down and left, the right side's pointing right and up. Okay. Last two, we made it to the end. Ooh, and we didn't even take up as much time as I thought. That's good. Example 9. Here's where we have ambiguity, right? As x goes off into infinity, I don't want to say infinity squared minus infinity is infinity because it's ambiguous. It's not really a fact. Okay, so what we're going to do is, yes, let us factor. Okay, let's use our limit laws. Let's call this f and let's call this g and do them separately and then multiply them together. The limit as x goes off into infinity, if the function is x, what's my limit? Okay. If the limit of x goes off to infinity of x minus 1, still infinity. So when I multiply them together, they're just going to blow up, right? So this tells me that the limit in general is infinity. Therefore, what is my conclusion? Yes, but what's my statement? What are we looking for in this lesson?
Continuity.
No, asymptotes. So no asymptotes. There we go. We are looking for horizontal asymptotes. This is technically H. There are no horizontal asymptotes because it goes on and on forever. Okay, let's look at our last one here. Limit x to infinity. What can you tell me about the bottom?
It can't be 3.
X cannot equal 3, which tells you what? We have a vertical asymptote at y, oops, x, oh, I keep getting my letters mixed up here. X equals 3. Okay? What can I do? What else can I do?
We can use the what's it called, the fraction of the highest degree.
Fraction of highest degree strategy, yes. Okay, let's do that. 1 over x times 1 over x.
Wait, why not? Okay, are we looking at the highest degree in the denominator?
Denominator,
Okay.
yes. Highest degree in the denominator. So this will give me x plus 1 over 3 over x minus 1. What term goes to 0?
3 over x.
Okay, so then I'm left with
Negative x minus 1 over 1.
okay, let's simplify that better. Simplify this into one line. Write it in one line for me.
Oh, negative x minus 1.
Okay, and as x gets arbitrarily large? Okay, some notes about the degrees and infinity. If we have the numerator greater than the denominator, notes on degrees, I should say, degrees of the polynomials. If the numerator is greater than the denominator, this will approach plus or minus infinity depending on coefficients. If the numerator equals the denominator, so for example, we have an x squared function and an x squared function in the bottom, typically this will give us a ratio of leading coefficients. And if the numerator is a smaller degree than the denominator, did I write that down correctly? Yes, smaller than the denominator, we will typically see it go to 0.
And we're talking about the degrees in the numerator and denominator, right?
Right. So, does what we just did match? The numerator is higher than the denominator, and it reached negative infinity, which matches, and the negative is determined by the coefficients. Okay, so here is just a little note card of information. You have lots of other note cards of information here. The distinction I really, really, really want you to note is the idea, where did I write this? This page on the front. You need to understand the difference between calculating the asymptotes that are vertical and horizontal. They are not the same. Please do not confuse them. It is one of the most common errors in this section, is confusing how to do the calculation for vertical and horizontal asymptotes.